Hi, I'm Dr. Paul Pienta, and we're doing the LeChatelier experiment for the GOB chemistry. LeChatelier is all about equilibrium, the shifting of the equilibrium when you disturb it. So you remember equilibrium is dynamic, and I like to think of it as a teeter-totter. You've got reactants, you have products, and they establish some balance point. If you disturb that equilibrium, if you add a product, that's going to move, it's going to go down here, and so it's going to shift to regain that balance point. If I add something, say, to the reactant side, let's say let's add more ammonia, then it's going to shift to the right to use up that ammonia and regain that balance of the equilibrium. It's always dynamic. Even when it's at the balance point, we're going forward and back, but the rate forward would equal the rate reverse. And so we're going to demonstrate that in several different experiments here, and hopefully you'll get a good feel for LeChatelier, the idea of shifting when you disturb that equilibrium. Part A, let's talk about that. This is the exact reaction we'll be doing. Copper with water attached, 4 of them. So we have a copper 2+, it's in the water, it's aqueous, and there are 4 waters literally attached to that copper. It makes sense because the water has lone pairs of electrons, the copper is 2+, and so they're going to be attracted. So it's surrounded by 4 waters. If we add ammonia, NH3, that ammonia can kick out those waters and replace them. So now we have the ammonias attached to it, you see, and the waters are let go. This is an equilibrium, so it's going back and forth, and I should be able to disturb it. And what's nice about this equilibrium is you can see it, because copper with the 4 waters is a nice light blue, whereas you put the ammonias in, it turns to a darker royal blue. So we should be able to see where this equilibrium is. If we have a solution that is all light blue, then we know mostly that equilibrium is lying over here on the left side. Whereas if it's more royal blue, then it's mostly on the right side. Chances are it's somewhere in between, and so we're not going to get totally light blue or total royal blue, but somewhere in the middle. As we add something like ammonia, we should see it shift. Now if we add ammonia so it shifts to the right, we should see the royal blue darken, increase. We should get more of that royal blue color. So let's go try. Okay, here I've got the protocol, just like you do in the lab manual. I'm just going to follow it right along. And it says step 1, add 20 drops of the 0.1 molar copper sulfate to a small clean test tube. So why are we doing, I'm going to use this test tube up here so you can see it against the white paper. Why are we using, by the way, why are we using copper sulfate? Because we can't just put copper 2+ in solution. There's no bottle of copper 2+. It's going to have a counter anion. The sulfate serves as that. So this is just a way to get the copper into solution. So 20 drops. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at some more. 1, 2, 3, 4, 6, 7, 8, 9, 10. Okay. Next, it says drop-wise add 1 molar ammonia, mixing after each drop until the color changes. Record the color and the number of drops of ammonia required. So here's my 1.0 molar ammonia, and we're going to, maybe the easiest way to mix this is for me to actually hold it. I'll also hold it in front like that, and we'll add some drops and we'll see what happens. Okay, so like 1 drop. Oh, we actually had a little bit of a change. I don't know if you caught that on the camera or not. Hopefully you did. Let's add another one. You see what's happening before I mix it. All right, so let's go ahead and stir that. Another one. Another one. Remember, you need to be looking at the color and counting the drops that are added. Another 2 drops going in there. Now we're getting a nice change. Let's go a couple more. 2 more. There's that nice royal blue that we were talking about. Let's go just make sure it's not going to change anymore. There's 2 more drops. All right, I think that's probably pretty good. And so there's that nice royal blue. Clearly, okay. Can't slide it in. Very good. So what have we done? We've added one of the reactants, ammonia, it caused LeChatelier shift to occur towards the products where we get the royal blue color instead of that light blue that we started with. Okay, step 3, it says now add 1 molar hydrochloric acid. Again, mixing after each drop until the color changes back and record the number of drops. So what is that going to do? Well, 1 molar HCl, that's going to neutralize the ammonia. Ammonia is a base, this is an acid, and when I neutralize that ammonia, it becomes an ammonium actually, but anyway, when I neutralize it, it comes off and the water should go back onto the copper, giving me my light blue color. All right. Once again, let me take it off so I can mix it easier. 1, 2. You can already see a little bit of a difference, hopefully. Swirl that up. Oh yeah, look at that. 3, 4. Wow, very cool. Nice, nice. Let's just add a couple more just to make sure. There's 2 more. I think we're just about right back to that nice light blue color. Okay. That is LeChatelier in action. Okay, let's do part B now. Part B, we have this equilibrium that we'll be looking at. H2PO4 with a -1 charge, that's dihydrogen phosphate, in equilibrium with monohydrogen phosphate and an H+. We see what's happening is one of those protons is coming off, going out into solution, leaving just 1 behind. We started with 2, we have just 1. That's a classic weak acid, acting as an acid, is donating that proton to give you the conjugate weak base. So this is an equilibrium. Again, I should be able to push it forward or push it backwards by LeChatelier type principles. Of course, I can add more of this, or this, or this. This is the easiest one to add because H+ can come from any acid. So I could use a strong acid like hydrochloric acid to increase the H+ and affect the pH. And I will remind you right here, pH is the negative log of the concentration of H+. And so if I change the amount of H+ that's around by changing the position of this equilibrium, I should see it reflected in the pH. For that matter, the pH scale, just a reminder, 7 is neutral. If I'm below 7 over here, this is my acids, just put it that way. Or if I'm above 7, this is what we consider the bases over there. Let's go see what happens then with this equilibrium. All right, here I've got the phosphate buffer and the hydrochloric acid that I can adjust with. Why does it say buffer? Because remember, a buffer is both the weak acid and the conjugate base at the same time in solution. So exactly what we have with that equilibrium. We have the one with the 2 protons, we have the one with just the 1 proton, right? The di and the monohydrogen phosphates, and so that's a buffer. Okay. So they're both in there right now in equilibrium with each other. All right, let's look at the protocol. It says step 1 there, well, step 5 here. Place 2 milliliters of that buffer solution in a test tube. Okay. 2 milliliters into a test tube. This is about 1 milliliter on my pipette, disposable transfer pipette. So let's see. There's about 1. Doesn't need to be exact for this experiment. And there's about 2. So that's fairly close to 2 milliliters. Okay. And we don't have a display. I'll just put it right there in the corner of my rack. All right, next check the pH of the solution with pH paper. All right, so we have our pH paper, which under different pHs, of course, changes color. And we see at the top there, 1 through 6, those would be the acids. On the bottom, 7 through 13, this one goes up to, those are the bases. Right. And as usual, to use this, you would tear off a little piece of paper and then have your solution, and you would touch it to the paper and see what color it changes. Okay, so we're going to do that with what we have in our test tube. Just to start off, let's see, and here we go. If you can zoom into that. Oops, I don't think I got just a little bit. Let's see if I can get a bigger drop hanging off of my. It's not, there we go. I was just using the wrong side. Okay, so we've got this greenish type color, which we can look up and see the scale. looks like just about a 7. Maybe a hair above 7, somewhere in that range. In the future, I'm not going to tell you that. In the future, we'll show you this, and it's up to you to decide, what is that on the scale? Okay. The scientist in me just wants to report that data right away. Okay. Now, let's see, next step. So add 1 drop of the hydrochloric acid, mix and check again. And repeat this up to 5 drops. So we're going to do this up to 1, 2, 3, 4, 5 drops and see how that affects the pH. Of course, adding H+, you would expect, well, maybe, there we go, 1 drop. Okay. Adding H+, I was saying, you would expect perhaps that it, mix it this way, that might be a little more thorough. You'd expect it to become more acidic. All right, let's see if we can get a drop here. And after 1 drop, there we go. There's the result. And you can compare it to the original one as well. And we're going to keep going here. We'll add a 2nd drop now. 2. Mix it up. Check its pH. After 2 drops. Good. Here's the 3rd drop going in. Okay. You can just stir it with that. That works just as well, right? Didn't get enough on there. Try again. There we go. Okay, here we go with the 4th drop. No, that was an air bubble. That was not a drop. There's the drop. Stir it up. Get a little bit more on there so you can see it better. There we go. And 1 last drop. Good. Mix it. There we go. All right. I'll let you look at that data. You might be surprised actually by the results. I don't know. There's the different colors after 5 drops of adding 0.5 molar hydrochloric acid. Okay, step 8 now says, hey, let's repeat this process, but instead of using the buffer, using water. So we're not going to have the phosphate, we're just going to use DI water and see what happens there. So there's some DI water. And the wash bottle here, get a different test tube. I'm just going to use about the same volume. I think I'll do it that way. So they're equivalent. There we go. All right. And let me rinse off my stirring now just to make sure we don't have anything else left over on it. And let's repeat the process. Plain water. I don't get that green color this one, right? This is a little bit different. Hold it up there, you can see the color. Okay. Now let's go ahead and add hydrochloric acid like before, drop by drop. So here's the 1st drop going in. Good. Mix it up. And look at that. A bigger drop. I can't get it to stick. Let's try that again. There we go. I think I got it. There we go. There's 1 drop. Put the 2nd drop in. There's air bubbles. I'm going to get them out of the way. 2 drops. sure that drop actually made it in the test tube. I wasn't sure, but it did. 3 drops. Four drops. And then finally, our last one, 5 drops. Okay. Put that up there so you can see the different colors. Clearly, the phosphate buffer reacted differently than the water. I'll just slide this along so you can kind of check the color of each one. And the water. Of course, the colors don't match perfectly. You get as close as you can when evaluating this. Okay? That is, without giving away exactly what's happened, that is LeChatelier. So as you think about how to analyze those results, remember we're talking about LeChatelier shifts. Okay, part C. Part C is dealing with a new equilibrium. That's up on this board. And specifically with something called spectator ions. So this is a longer one, but let me step you through it. We've got iron in the 3+ state, chloride, potassium ion, thiocyanate. 4 of those combining together to give you iron thiocyanate, so there's the complex, and then, oh, what's this? 3 chlorides and potassium. If you notice, the 3 chlorides are the same on both the left and the right side, and the 1 potassium is the same. In other words, those are called spectator ions. They're not contributing to the reaction, but they are in solution. They're in the beaker along with the other things that are actually part of the reaction. The ones that are reacting are the iron and the thiocyanate combining to give you the complex. And we can tell what side of the equilibrium we're on because the iron by itself in solution is yellow, whereas in the complex with the thiocyanate it is red. So if it was all here on the right side, we'd have a red solution. If it was all here, a yellow solution. Again, we're probably going to be somewhere in the middle perhaps. It would be more orangey, right? If it turns more red, we know it's shifted to the right. If it turns more yellow, it's shifted back to the left. Okay. Now, that's the usual, and we'll do that first. We'll see where we're at. We'll check the color out. Now, the spectators usually have nothing to do with that. In fact, you can even cancel them out and not even put them in there. All right, so why are we even considering them in the first place? Because that's how we got it into solution. We start off with iron chloride, like that. That's the solid form that we actually get. And the same thing here, we get from this the stock form, I'm saying. Potassium thiocyanate. That's how we get it, and then when we put in solution, of course they separate into the positive and the negative, and those parts combine with these guys, they're just hanging out, and they're not going to get combined, they're just spectators. Okay? So that's why they're there in the first place. Now the interesting thing about the spectators with this one though, is that if you get it at really high concentration, so if we put a lot of that spectator chloride in solution, it actually starts to compete for the iron, compete with the top reaction that is. And here's what it looks like. Iron plus, if you have excess chloride, it combines to give you this complex, iron with 4 chlorides around it. That's yellow, of course, and this is colorless, no colors at all. Right? And so that only happens when you have a really high concentration of the chloride. So we potentially have 2 reactions happening. This one's definitely going to be reacting even at low concentrations. If we get that chloride up high enough, then this will also start to react and occur in our solution. So let's go give this a try. Okay, step 1, it says in a 50 ml beaker, we have a 100 milliliter, that's fine. Let's go here, it might be easier to see. It says combine 1 milliliter of the iron chloride, of the iron 3 chloride, which I've got here, the potassium thiocyanate, which is there, with 50 milliliters of water. All right, so let's start with the water. Let's pour this over.
milliliters. And we don't need to be terribly precise here. That's 45-ish. Let me just count it down. Get down even with your eye so you can see what's happening. And there's just about 50. Okay. We'll put that in the beaker. That's just our water, deionized water. And then 1 milliliter of each. And once we get all of that in the beaker, that will be all of the things on the left side of our initial equilibrium. So here's the iron chloride. And 1 milliliter gives, again, is just about, you can approximate it to the, oops, get down in the solution. There we go. That's about 1 milliliter right there. Okay. And yeah, you see it's kind of got a yellowish tint to it, very pale yellow. You just see it. That's that iron in solution. All right, here's the potassium cyanate. Oops, gotta get a little more than that. All right, that's just about 1 milliliter. We'll add that. Ooh, that was pretty. Clearly, something's happened there because it was clear going in, but man, when it hit that, it turned this nice, dark, orangey type color. So again, I wouldn't call that red, I wouldn't call it yellow, it's somewhere probably in the middle, kind of an orangish color. And again, that just reflects the fact that we have an equilibrium, we have both the left and the right side of that reaction happening. Okay, there it is. Let's see, next it says to each test tube, or we transfer, yeah, we got 4 test tubes laid up there. To each of them, put 2 milliliters of this solution. Okay, so we're going to put 2 milliliters of our solution in each one of our test tubes. And again, that's 1 milliliter there. So let's see, there's 1. A little more than that. There's 2. It's really kind of a pretty color. This orange solution. This is not quantitative, and so I'm not worrying about getting exactly 2 milliliters, that's okay. We're looking for color changes, and that's just qualitative in nature. Okay. Okay. Very good. So there's our 4 test tubes. And we'll go back to the board here for a second. Just to remind you, what we have in those test tubes right now is that top equilibrium. We have, the spectators are not doing anything with that solution yet. And so we essentially just have the iron plus the thiocyanate combining to give you the complex. And again, this is yellow, this is red. Our solutions are orange because they're somewhere in the middle. That is to say, both the left and the right side is present at the same time. All right, let's come back here. And on each one of these test tubes, we're going to try to tweak it. That is to say, we're going to add a little something and watch LeChatelier hopefully cause a shift. The first one, it says add 10 drops of just water. Well, why are we doing that? If we're going to be looking for color changes and we're adding 10 drops of solution, that does dilute it a little bit. And so this orange will whiten just a hair just because of a dilution. So step or test tube 1 is our control to see what that looks like. So 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Yeah, and you can see it is just a little bit lighter than the other ones. So that's what we're going to compare to. Water is not part of this equilibrium. And so by adding water, I'm not causing LeChatelier. It's not shifting, it's just being diluted a little bit. And so it's slightly lighter orange. The other ones we're going to compare back to that test tube number 1. All right, test tube 2, add the iron chloride solution. So here, it's one of the reactants. If we add a reactant, LeChatelier says, hey, we should get a shift. I'll let you think about which way that goes. So here is test tube number 2, 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hopefully you can see that color definitely did change. And you can think about whether that is consistent with LeChatelier and what you might have predicted or not. Now the other reactant, the thiocyanate. 10 drops of that into test tube 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. So far, we haven't put any excess of the spectator yet, right? We've just done the iron, we've done the thiocyanate, and so for the test tube number 4, here's saturated sodium chloride. So this is very high concentration of the chloride, Cl-. This is the spectator that we were talking about, and we're going to add 10 drops of this, which will be adding a whole bunch more of that spectator. Let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let's just zoom in on those test tubes and look at the differences of the colors. As you think about what you're seeing, again, LeChatelier is what we are investigating. So think about which way it caused that equilibrium, or in this case, the two equilibriums, to shift. Okay, part D, our final equilibrium. We're going to look how temperature can actually affect the equilibrium. Let's go to the board. For this part, we're looking at a cobalt complex, cobalt in solution with 6 water, so this would be cobalt hexahydrate in solution, plus chloride. The chloride kicks out the water, so now I've got cobalt with 4 chlorides surrounding it, this new complex, and the water's got kicked out. This is, again, an equilibrium, so they both can be present at the same time in the solution. The one with the hydrate, with the water, is a pale rose color. The one with the chlorides is a more purplish color. Not a dark purple, but it is more purplish, which you'll see. Right? And so, initially, we're just going to make this equilibrium. Right? We'll add this via hydrochloric acid, and hopefully we'll see that color change from a rose to a more purple color. Let's do that at time. I've got my water bath for the second part. We're not going to use that initially. Okay, so here's my 2 solutions. Here's the cobalt chloride, just to get some cobalt into this actual test tube. All right, and they said to add 5 drops of that. So here's test tube 1. 1, 2, 3, 4, 5. Okay. And I'll hold it up here against the good light. You can see what color that is. Okay. Now, we will add the hydrochloric acid until we see a color change. So I guess I'll hold this up here. Hopefully you can see. Is this in the way? Maybe make that a little easier for me. Okay. Adding the hydrochloric acid is a good source of that Cl-. And so there's 1 drop, 2 drops, 3 drops, 4 drops. You can start seeing a color change there. 5 drops, 6 drops. That is the more purple type color. I'll do 1 more drop. 7 drops, just so you can see that well. Okay. So that I'm going to go ahead and put here so we have that as a reference for what that looks like. So we've seen now both the left and the right side of that equilibrium. Go back to the board. We saw that initial pale rose color when you had the cobalt in solution. It had water surrounding it. And then we added the HCl, the chlorides, and then we saw that purple cobalt chloride complex. And next, we're going to investigate how does that change with temperature. Is it endothermic or is it exothermic? So is that reaction absorbing heat or is it releasing heat? All right. We'll do that by just not even worrying about the hydrochloric acid. We're going to add just a milliliter of the copper chloride solution, which has chlorides out in the water already, right? Just doesn't have a lot of them. And we're going to add heat to it by putting it into our boiling bath. So here's about a milliliter of that solution. Again, you can see the color, and you can see the color compared to the one where we've driven it over to the product side. This is pale rose, where the other one's purple. And now we'll take this and put it down into our water bath. see the color change. Takes a little bit of time for the test to warm up, but hopefully you can see that changing color already. We'll give it a couple seconds here, maybe another half a minute. Keep it nice and hot. That's good. So I'm going to pull that up here. And now you can see the comparison. And actually, as it's cooling off, you can see the colors changing back again to the original color. Very interesting. So, heat is affecting the position of the equilibrium. Technically, that's not right. You want to know the technical, it's changing the value of K, the equilibrium constant, which changes the position of the balance of the equilibrium. But I don't want to get into that. LeChatelier, you can think about it in terms of LeChatelier as well. On the board, we added heat to this equilibrium. So you can think of that as adding heat. It's either going to come in over here on the left side, adding heat, that would be endothermic, and adding heat would then drive it to the right side. Or, if this reaction is exothermic, it would be like adding the heat over here. And therefore, when we make it hot, it would drive it back to the left side of the reaction. So, given the color changes that you've seen there, you could determine whether we had an endothermic or exothermic reaction.